It's 2004. The DVD is overtaking VHS for home viewing pleasure. The CD-ROM is reigning king as the gaming storage medium of choice, and USB sticks are becoming affordable for moving data from place to place. The average game now consumes hundreds of megabytes in storage, but despite this, Squarespace have sponsored this video. Oh, and somewhere in Europe, a team of developers have created a first-person shooter that will fit in under 100 kilobytes. 96 kilobytes to be precise, or if you'd prefer, 96,000 characters. How in the holy land of smeg does a shooter like this fit not just once on a floppy, but 14 times? To put this into perspective, the original 1993 Doom shareware consumed around 4 megabytes of disk space. The original Duke Nukem took up about 1 megabyte. This PDF document that contains the script of this video consumes 104 kilobytes. This literal screenshot of Krieger, well, that consumes 96.1 kilobytes. Seriously, there it is in the file system. What gives? To answer this, we have to go back to the year 2000 and visit the demo scene. Of course, the demo scene had been around for many years before this, but we're interested in a German group known as Farbrausch, the members of which had been involved in the demo community for many years already. But on the 29th of December 2000, at an event in Denmark known as The Party 2000, a meetup where demo teams got together to show off their latest and greatest real-time productions, they pushed out a demo they called FR08 TheProdukkt, and it was mighty impressive. The product was not only fluid, incredible looking, and filled to the brim with shading effects, transparencies, lighting, eye-arousing textures, and a thumping soundtrack to boot. It also compacted into just 63.5 kilobytes. Think about that. This demo could technically fit into the memory of a Commodore 64. That's staggering. Of course, it wouldn't run on a Commodore 64, in fact it needed a pretty beefy PC at the time to run it smoothly. And that indicates a bit about the trickery going on, because despite its diminutive initial size, the full 11-minute demo produces the equivalent of 159 megabytes of waveform data, 170 megabytes of textures, 80,000 coloured and textured triangles in 5.7 megabytes of static vertex buffers, and a crap ton of animated geometry, all in totaling 1.9 gigabytes of data, all from a file just under 64 kilobytes in size. That would equate to a compression ratio of 30,000 to 1 if all this data were literally compressed. But of course it's not that simple, and that would be one hell of a compression algorithm if it was. So the demo label Farbrausch, who also masqueraded under the company name TheProdukkt, spelt with 2 Ks, consisted of several members: giZMo, Chaos, Fiverr2, KB, Dodge, Rig, Wayfinder, and Yoda. It was Fiverr2 who first realised that only a few primitives and filters were required to create realistic looking textures, and so created a set of building operations based around these. From this, a couple of basic patterns could be used to generate hundreds of seemingly different and realistic looking surroundings, from what was essentially just a macro. Procedural generation. and if you look throughout the demo you'll see names applied to textures which indicate the type of operations applied. These parts of the code were created in assembly language to aid with speed and code size, whilst the remainder was created in C++ due to its useful combination of low and high level componentry. The music created by KB is just a compressed down MIDI format which just tells the sound card what instruments to play and when. Essentially this is music already in macro form. Farbrausch demos would increase in complexity during 2002 and 2003, including FR19, Poem to a Horse, and FR30, Candytron, which included character animation and vocals, again all in 64K. But the seed for a fully playable FPS had been in the team's minds since 2001, and in fact FR30 Candytron incorporated the same codebase that would be used for that project. By January 2004, in the words of Rig,
"We had been working on it for a long time and badly needed a break, but we also didn't want to go to Breakpoint with empty hands, so we had to release."
Breakpoint 2004 is a huge demo scene event in Europe and was set for April the 9th to the 12th. It happened to include a 96KB game competition. It was this competition that their 3D modelled FPS, Krieger, would be entered into and triumphantly win, quickly going on to become an internet sensation. And let's be honest, going viral on the internet in 2004 was no easy task. Krieger, by the way, is German for warrior, and it certainly won this battle. So how was this heroic feat pulled off? Well, Krieger relies on some of the tools and tricks of Farbrausch's earlier demos, but there's a huge difference between a non-interactive demo and something that you can not only interact with, but actually play and advance through. An interactive experience has to be ready for you to look in any direction, at any time, to be able to walk close to objects, to walk away, to activate doors, and obviously to provide weapons and foes to beat down. But just like demos, it's the textures which traditionally take up the most space. FR8, TheProdukkt, used an in-house developed tool called Werkkzeug to create these textures. Krieger used an updated version, Werkkzeug 3, and it's incredibly clever. Here are 3 patterns. Pay close attention because these 3 simple patterns, which are created from scratch using an algorithm every time the game is run, were the basis for every single texture in Krieger. But how do you get from this to this? Well, you create routines which replicate some of the well-known Photoshop filters and deformations, such as blur, twist, bump map and distort, add some color correction, change the tint, contrast and hue, and already you're getting somewhere close. The clever bits come in the form of, say, applying a blur filter, then subtracting the original image and modifying the brightness. Now you've got an outline that can be multiplied and rotated with other outlines, and soon you get some pretty complex looking textures, all without anything pre-rendered at all. This wood texture was created using those exact methods, a combination of noise filters, blur, twirl, and color distortions. Same with concrete and stone, starting from different base patterns. Importantly, because these are all rendered in real time, it doesn't matter what resolution or how far you zoom in, the game engine will automatically accommodate for the difference and show these real-time textures in distinct clarity. In fact, there's often so much detail in these textures that your mind glosses over them, and this is actually noted as a fault by Fiverr2 and giZMo, discussed in a 2004 assembly presentation. But before that, the same is true in designing a lot of things, including websites. That's why Squarespace has a multitude of clean and clear templates for you to choose from. If you've got an idea that you want to grab people, then you don't want it to get lost because of poor design choices. Just look at all these templates you can choose from. Just pick the one you like and then effortlessly make it your own. Squarespace allows you to turn your site into a blog, a shop, a showcase, whatever you want. You can even use it to set up email campaigns. You could get started as soon as this video is over, and then grab 10% off your first website or custom domain using the link below.
And another thing is the textures simply have too much contrast. Every single texture is so full of details that in the end it's there's so much different detail that it looks like no detail.
Another clever trick is to employ standard Windows libraries and even fonts. This texture, well, it's just the letter G in the Arial font with a twirl, noise and bump map applied. To get more complex and structured textures, you can just combine some of these simpler tiles, use multiplication routines, and make use of alpha channels to create the defined objects that you need to replicate a sewer, for example. This on-the-fly creation means that the game actually expands to occupy about 300 megabytes of memory when running, which is more typical of an actual FPS game from this era with prefabricated graphics. And that's because once the graphics are actually created and posed to us as images, well, they consume the same amount of memory as the image would. In addition to the lack of large assets, clever use of the standard Windows Dynamic Link Library set for window management, graphics and memory allows a lot of code to be farmed out or outsourced, saving space that might usually be taken up with custom code. Naturally, this includes the use of Microsoft DirectX, which was utilized extensively, including its lighting model and pixel shading abilities. In fact, these could be combined with texture bump maps to create accurate lighting effects with minimal further work. It's for that reason that you'll find bump maps employed throughout the game, even when they're not strictly necessary, such as on weapons, as it just creates a more pleasing level of light reflection. But what do all these textures wrap around? Well, that's the job of mesh generation. Using 3D objects such as cubes, spheres, and cylinders, textures can be applied, and then similar deformation procedures can be applied to these models. One of these is a simple bend. It just creates a much more realistic environment, and that's why you'll see long, winding environments in this very linear game map. The use of a linear level, again a space-saving necessity, but the winding and bending of it creates the illusion of a more diversive playfield. All these elements are applied in Werkkzeug using operators. Some operators will create meshes, some will create textures, others will apply effects like blur and bump, others will apply distortions or add bends. Everything is an operator, and by stacking these operators on top of one another and forming connections in the operator stacking environment created by Chaos, it provided a visual way of creating the world, which could be seen in real time through a preview window. This is actually version 1.2 I'm using, and you can see how I can add particle operators with transform operators, a material operator, and finally some camera and time operators to make the view spin around and get this output. Tools like this sped up the development process massively, producing lightweight, efficient code without creating it from scratch. The beauty is this tool can be used for almost everything in the game engine, including characters. The character models draw from FR30 Candytron, and again employ the use of primitive shapes stuck onto one another. The operator stacking system could also be used to manipulate shapes, combined with movement operators to create fully animated models. the only problem being the movement was mostly based on linear ramps, such as pivoting a leg forward, pivoting the next leg forward, and so on, but it looked janky and dated, or in their words, like N64 character models.
This is just like N64 style, what they stick primitives together, and we are far away from that nowadays. But
I mean, come on, it's 2004, we're way past that. The solution to this was to introduce trigger operators. For example, if you move a leg forward, an arm movement would then follow. This allowed for slightly better looking characters, and it's also why the foes have massive arms or multiple legs. By drawing more attention to these reactive elements, these creatures look more natural and flowing than if you witnessed just singular leg movements. Now, although all the textures are created in the initial loading sequence, which saves some processing time, there's still a lot of real-time processing going on. So we've got character-based animation and the complexity of the world, and this meant you'd need something pretty beefy to run it. Like an Intel Pentium 3 clocked at 1.5 GHz, half a gig of RAM, and an Nvidia GeForce 4 Ti. We're talking high specs for 2004, but boy, was it worth it. Well, kinda. We can explore the gameplay a bit later. Okay, so that's most of the space saving taken care of, but we're talking compressing all this into 96 kilobytes. This means that even with the textures done away with, the coding itself needs to be ridiculously small and compact, and for a team of developers and designers working part-time, this fact alone meant the game almost didn't make it into the competition at all. In a post entitled Metaprogramming for Madmen, the Rig blog details the endeavour from Fabian Giesen's perspective, and you can feel the intensity of those last few weeks bursting through the pages.
While being a nice technical challenge, it was a complete failure as far as the game side was concerned. We very nearly missed the 96K limit too. Our most serious 64K demos were somewhere around 70 to 80K a few weeks before they were supposed to be released. The last 2 weeks usually ended up turning into a frenetic rush to simultaneously get the thing actually finished and make it fit within the size limit. There are 3 different steps to making sure you get small code. Architecture. Design the code in a way that enables it to be small. Evicting ballast. There are going to be whole paths of code that are just not getting used. Detail work. It basically boils down to figuring out which functions are larger than they should be and what you can do to make them smaller.
I actually had a chance to speak to Fabian about implementing the architecture, and specifically the 3D engine, the code of which is available on GitHub, and although the coding was a crucial element to get right here, he downplayed its significance in terms of game engine compared to the graphical work. Ultimately, it boils down to having some arrays in memory the GPU can access, and then periodically giving the GPU a command to draw from these arrays. Due to the limitations of the Pixel Shader 1 hardware, it was imperative to have a robust system for sorting draw commands, and efficiencies could be made through the level design. Because levels are just a series of connected rooms and corridors, anything not in the player's room can only be seen through a doorway, meaning a lot of the world didn't have to be redrawn. Really, the main bulk of the 3D engine is memory, resource, and lifetime management, and getting these as trim and efficient as possible. This is almost all standard C++ code, compiled in Optimize for Size mode, and making use of Visual C++'s function level linking, which puts each function in its own section and only links and compiles functions that actually get referenced, which we'll get to in a bit. Chunks of inline code are written in assembly, along with the inclusion of assembly source files, mainly for speeding up and to reduce dependencies, negating the need for chunkier C++ libraries. Interestingly, most of the development time was actually developing the tools such as Werkkzeug for artists, Fiverr 2 and giZMo to use. It's also interesting to note that Krieger was made on the cusp of systems moving to 64-bit, And one of the biggest constraints faced by the team was the 2 GB limit of 32-bit systems at the time. Given that the tools and content editing would consume 1.5 GB of RAM alone, with another 400 MB for the game to run on top of that, these guys were really up against the limits of conventional desktop PCs at the time. This might be a 96 KB game, but it chunks out hugely when written into memory. So the architecture itself could be developed fairly normally, but the next part, evicting ballast and the detail work, would be crucial in getting under size. The first playable versions of Krieger were 120 KB, so it was down to these steps to shave off those extra few precious KB. And a lot of it had to be done pretty close to the wire, again by developing tools to do the heavy lifting. So in the final days, with time rapidly running out, Chaos created a parser named Lector to go through the C++ code and essentially find anything that was redundant, and broadly speaking, here's how that worked. Okay, so here's an if statement. Now you'll have to forgive me, this is pulled from Rig's blog, but it's been a while since I was knee-deep in any form of C coding, thankfully. But the parser would run through each statement, numbering as it went, leaving a trail of breadcrumbs. This would highlight any parts of code that weren't being executed. In this if statement, it was determined that MSM sub and MSM set not only get called if the variable state is true. Therefore, the if statements nested here are redundant. That code would then be replaced with if 0 if the path is never taken, or if 1 if it's always taken, which essentially renders each if redundant. So simplifying, this find and replace operation would work through the entire code, and then upon compiling into an executable, the compiler itself would recognize these issues and strip out the logic queries completely, because they were redundant, therefore saving precious bytes. Things like this were done with a fine comb throughout the entire code to shave those extra few kilobytes off. As you might imagine, the upshot of this was that actually it forced a few bugs into the game, because to determine the paths which weren't executed, the game had to be tested, and during that testing, if no one decided, for example, to try pressing the up arrow on the menu screen, that pathway to trigger the action would be stripped out, meaning you could no longer press up on the menu screen. It also meant that some collision detection was removed, as it was never triggered during test runs. These issues did actually creep into the first compacted versions, and some remained in the released beta. Basically, this was code stripping at its most desperate and also dangerous. The final step was to use an executable packer to compress the file down as much as possible. In this case, an in-house utility called Crunchy, which utilized a similar compression standard to zip files, but had extra functionality, like being able to tell you how well certain coded functions would compress, allowing final tweaks to be made beforehand. Okay, look, this is dramatically oversimplifying it, because crunching down or packing an executable has been one of the most important and intensively developed parts of the demo community for years. How do you think Cracker's got so many games on a single floppy disk? In Crunchy's case, the magic is performed by a number of factors, but there's a package created by Rig called disfilter, which disassembles the binary x86 code and compacts the LZMA compression by an extra 20% on average. But compression is an entire subject in itself, so what's important here is that this cruncher is what got Krieger under the required size. The upshot of all of this was that the game came in at just under 96 kilobytes in literally the final hours before the competition deadline, allowing it to grab the event and indeed the internet shortly after by storm. I mean, come on, this is an incredible feat of problem solving, design and coding, especially for a team working solely in their spare time. So of course we have the odd bug such as getting stuck indoors, enemies getting stuck, and there are lots of elements that the team wanted to improve upon, including the addition of light maps, better level design, a brighter environment, and the textures having less contrast. But it's playable, it feels coherent for a shooter of that era, and it definitely looks very good. What I find really interesting is how Thomas says he almost felt like he was peering into the Matrix by the end, seeing the real world just like Krieger as simply being made up of algorithms and mathematical shapes and models, which of course it is. If that's not food for thought, I don't know what is. Unfortunately, although promised, an updated finished version of the game with multiple levels never emerged. This version was hoped to clock in at about 120k, but given the cat was already out of the bag, anything released afterwards would have been anticlimactic, and I completely understand why the team never felt enthused enough to revisit it. That's not to say they didn't do any work on it though, and indeed some source code does exist for Krieger Final. I'm actually talking to Rig about getting a version of it up and running as I type this. If that happens, stay tuned on my second channel for a playthrough because that will be incredible. But ultimately, it was an experiment. These were demo scene coders who enjoyed the thrill of creating something that pushed the limits of the current hardware, that dazzled the senses. And although Krieger had certainly done that, the gameplay aspect of it was really more of a novelty than anything else. It was hoped more could come of it, and TheProdukkt did attempt to package up Werkkzeug and the Krieger engine to sell it commercially, but I get the feeling that the team weren't really behind this idea, and in fact Rig spells that out clearly on his blog. The demo team did make a few more creations, including the incredible FR41 Debris, which clocked in at just 177 kilobytes, but TheProdukkt as an entity was officially disbanded in 2011, leaving Krieger as an incredible showcase at a time when most games were enjoying the new freedom of cheaper storage and getting larger rather than smaller. This whole experience really makes me miss the bottlenecks of older systems, I mean even more so than I already do. They demanded that developers be much more efficient and creative with their visions than the more mindless high-level freedom that current technology offers. So I find it soul-warming that demo scene coders were still propelling these ideas forward into the noughties and even still into today, whether it's to save space or just speed up a game engine. It's just fascinating to be given constraints and then create something as impressive as possible with them. That's what Krieger does, and it's why so many of us, myself included, adore the vintage hardware and the limitations it still imposes. I've been Nostalgia Nerd. Toodaloo.